If you look up at the sky on a quiet afternoon, the atmosphere seems almost still, but in reality, you are looking at the bottom of a massive, shallow ocean of air. This ocean is constantly in motion, driven by the heat of the sun and the rotation of our planet. For most of human history, predicting what this fluid would do next was a matter of folklore and intuition. We looked for patterns in the color of the sunset or the behavior of birds. These methods weren't entirely baseless. They were early forms of pattern recognition, but they lacked a fundamental understanding of the physics governing the clouds. The transition from lore to science began in the 17th century with the invention of the barometer. Suddenly, we could measure something invisible, air pressure. Scientists like Robert Fitzroy, who sailed on the HMS Beagle with Charles Darwin, realized that these measurements could be shared across long distances using the newly invented telegraph. In the 1860s, Fitzroy began collecting data from coastal stations to warn sailors of coming gales. He coined the term forecast. His methods were simple, drawing lines on a map to connect points of equal pressure, but they represented the first time we treated the weather as a physical system moving through space. By the early 20th century, a mathematician named Lewis Fry Richardson imagined a way to turn weather into a math problem. He believed that if we knew the current state of the atmosphere and the laws of physics, we could calculate the future. In 1922, he attempted the first numerical forecast by hand. It took him 6 weeks to produce a 6-hour forecast for a single location, and it was wildly inaccurate. He dreamed of a weather factory, a massive stadium filled with thousands of people, all calculating small pieces of equations in sync. He was right about the method, but he was decades ahead of the technology required to execute it. The arrival of the electronic computer in the 1940s finally made Richardson's dream possible. The ENIAC, one of the first general-purpose computers, was used to run the first successful automated weather model. These early models treated the atmosphere like a series of interconnected boxes, calculating how air moved from one box to the next. As computers became faster, the boxes became smaller and our accuracy improved. We began to think that if we just had a powerful enough computer and enough sensors, we could eventually predict the weather with total certainty, weeks or even months in advance. That dream of total certainty was shattered in 1961 by a meteorologist named Edward Lorenz. While running a weather simulation on his computer, he decided to repeat a calculation. To save time, he entered the starting data rounded to 3 decimal places instead of 6. He expected the result to be nearly identical. Instead, the small change led to a completely different weather pattern. This was the discovery of deterministic chaos, famously known as the butterfly effect. It revealed that in a system as complex as the atmosphere, the smallest uncertainty in our measurements grows exponentially over time, eventually making a perfect long-term prediction impossible. To understand why the math is so difficult, we have to look at the Navier-Stokes equations. These are the formulas that describe the motion of fluids, including the air we breathe. They are notoriously complex because they are nonlinear, meaning a small change in input doesn't produce a proportional change in output. Even today, mathematicians haven't fully proven that smooth solutions to these equations always exist in 3 dimensions. Because we cannot solve them perfectly, we have to use approximations. We break the world into a 3D grid and simplify the physics within each cell, which inherently introduces small errors into every model. Today, we manage this uncertainty using something called ensemble forecasting. Instead of running one single model, supercomputers run dozens of slightly different versions at once. Each version starts with a tiny variation in the initial data simulating the butterfly that we might have missed. If all the models agree, meteorologists can speak with high confidence. If the models diverge wildly, we know the system is highly unstable. This is why you see percentages in your weather app. A 30% chance of rain doesn't mean it will rain in 30% of the area. It means that in 30% of the computer simulations, rain occurred. We are now entering a new era where artificial intelligence is beginning to augment these traditional physics-based models. Machine learning algorithms can look at decades of historical weather data to find patterns that the standard equations might miss. These AI models are incredibly fast, capable of generating a global forecast in seconds on a desktop computer, a task that takes supercomputers hours. While they don't replace the laws of physics, they offer a different way to bridge the gap between what we see now and what will happen tomorrow, potentially extending our window of accuracy by a few more days. Despite these advancements, the chaos limit remains. Because we can never know the position and velocity of every single molecule in the atmosphere, our forecasts will likely always hit a wall around the 2-week mark. Beyond that, the chaos of the system simply overwhelms our data. This isn't a failure of science, but a fundamental property of our universe. We have learned to live within this uncertainty, using genius math to turn a chaotic sky into a predictable tool for agriculture, aviation, and daily life. We may never predict the weather perfectly, but we have mastered the art of listening to the chaos. In the end, weather forecasting is a testament to human persistence. We took a system that is inherently unpredictable and found a way to see into its future, if only for a little while. From Fitzroy's first storm warnings to the massive silicon brains of today, we have moved from guessing to calculating. The atmosphere remains a wild, fluid thing, but we no longer stand beneath it in total ignorance. We have built a bridge of mathematics across the clouds, and while it may not reach the horizon, it is enough to guide us through the storm.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.